Here we go, computer science, Barron's Unit 8, searching and sorting, the final unit. Okay, I took you guys' questions. I think 9 out of 21 of you had made requests. So, whatever. Numbers over here are number of people who have asked for them. I'm probably just going to go through all of them and talk about how to do these. So, a lot of these are tough. You got to understand searching and sorting algorithms. You're not going to have to write your own for your response, but you need to understand these for multiple choice. Understand their weaknesses and their strengths and how they work. The decision to choose a particular sorting algorithm is based on runtime, how quick it does, the size of the array. Some of them work better for shorter arrays, some for longer arrays, and space efficiency. Like you got to be conscious of space. So all three of these are very good things to consider when picking a algorithm. Okay, following code fragment does a sequential search, which is where it just looks through the whole thing until you find a certain value. It doesn't have to be in order. Starts at 0 while something is true, increment this, and then if we finish, once the while loop is done, if it equals n, that means we got through the whole thing and therefore didn't find it. Return -1, which is a common return for when you don't find something. Otherwise, return I, which would be some spot. Now, n is the size of the array, but it is not the last spot. It's beyond it because we start at 0, so we got n minus 1 is the last spot. That's why it's not the last spot in the array. Which of the following should replace the Boolean expression so the algorithm works as intended? Well, we need to check if the current spot equals what we're looking for. So you need a value equals a whatever I we're at, and if you want the while loop to keep going if it hasn't found it. So we want not equal to, not equal to, not equal to. Because if it is equal to, then you're done and you skip down here. The other thing you got to watch out for is that you don't get array index out of bounds, which is going to happen unless you put some check to make sure you haven't gotten to the end of the array. Now, can we check before or after? Does it make a difference? It needs to be an and thing. Okay, so definitely not or. But we need to check before, because if we check after, then we're going to try and access the at spot in the array before we check to see if we're still within the size of the array, and we're going to get the index out of bounds. If we check this first and it's false, it doesn't even look at the next thing. It's called short circuit evaluation. And that's what Java does with these compound, these multiple comparisons. It'll check the first one. If the first one, on an or is true for sure, then it doesn't even look at the next one. If it's first one's a false on an and, then it won't even look at the next one. So then that way you can kind of keep things from giving you errors. A feature of data that is used for binary search, but not necessarily sequential search. So what does binary need that sequential doesn't necessarily need? Does the length of the list matter? No. I mean, one can be better or worse, but doesn't need it. Type of data? No. Order of data? Binary needs it to be sorted. Sequential doesn't. So binary needs sorted. Sequential doesn't need it, but can take advantage of it. If you read, if we know it's in order and you're doing sequential and then you didn't find it and you're at the next one that's larger, then you could just stop your search without searching through the whole thing if you know it's in order. So sequential can take advantage of it, but doesn't need it. Median value of the data, no. Smallest value, no. So there we go. Number 4 says unsorted array, unsorted list, sorted array, sorted list. Which of the following operations is more efficient for sorted than unsorted? Inserting a new element. It doesn't say inserting it in order. So we can just insert this wherever we want. So that's, that doesn't make the sorted one better than the unsorted one. Searching for an element. Yes, searching through a sorted array is much easier than an unsorted array. Computing the mean, we just add them all up and divide by the number. Neither one of those has an advantage over the other, so it's going to be 2 only. Number 5, an algorithm searching a large sorted array for a specific value compares every third item in the array to X until it finds one that is greater than or equal to. When a larger value is found, the algorithm compares X to the previous 2 items. So it's like skipping every 3 to kind of like break it up. If the array is sorted in increasing order, which of the following describes all cases when this algorithm uses fewer comparisons to find X than a binary? Now, binary is pretty efficient. It cuts in half. And it does it in about as many comparisons as this equals the size of the array. It will. So will this new method of skipping every 3 be better than binary? Use less comparisons? It will never. No. If X is middle, this is best for binary. This is actually the best for binary. Binary finds it the first time. X is very close to the beginning. Yes, because we'll find it sooner if it's near the beginning. Binary could end up doing its worst case scenario potentially. X is at the end. No, binary is going to probably win. X is not in the array. No, binary is going to win in that case. So, C. Let's see. Number 6. Assume 0 to an array of n positive integers of the following is true. So, n positive integers says that 0 spot is bigger than the kth spot, where k can be anything from 0 to n. So that just means that this is the biggest thing. It's bigger than all of the other spots, right? So which line must be true? The array is sorted? No. First of all, it wouldn't be ascending. It might be descending if we start at the biggest, but we don't know what's true about the rest of it. We just know the first one's the biggest. Descending, don't know that. I mean, this one's no. Could be. All the values in the array are different. We have no clue. Well, that one's at least bigger than all the rest, so that is for sure false. There's at least 2 different, because it didn't say or equal to. A0 holds the smallest. Nope, it's the largest. So there you go. Number 7, the following code is designed to set index to the location of the first occurrence of key in the array. Okay, -1 if it's not there. So it sets it to 0, and it says, while it's not equal to it, let's keep looking. And until it finds it, then we're done with the while loop. And then after that, it says, well, if this doesn't equal key, then it must not be there. So we'll set it to -1. In which case will this program definitely fail? Now, the thing you got to watch out for is it's checking, but it's not doing a check on the size. So we could potentially get an out of bounds exception. So we need to actually, in front of this, be checking the size. We need to make sure that index is less than the size of the array. So I don't know, I'm going to do a dot length, right? And so we can get out of bounds. Now, it's not guaranteed we're going to get out of bounds, but if we don't find it before the end, if it's not in there, then we're going to get out of bounds. When key is the first element, it'll fail. No. When key is the last element, no, it'll find it. When key is not in the array, we're going to get problems, right? So you got to make sure we don't get out of bounds there. 8, consider the following class. class that sorts an array of integer objects from largest to smallest, descending order using selection sort. Selection sort looks for the biggest thing and swaps it. And then it looks for the next thing. It has to look through the whole rest of the array every time. It's not super efficient for large arrays. So we have private instance variable that holds integers, capital I, integer objects. It's called sorter. This is a constructor. It has a swap method, which it doesn't show you, but that's a common method. It copies the current spot into a temporary variable and then copies the other one into that and puts the temporary back in there, and it just swaps two spots. It's common for several algorithms, so it'd be good to look back at the code that makes that work. So we're going to sort an array from largest to smallest using selection sort. So descending order. It starts at I equals 0, and it keeps looking. Now it skips the last spot. And if you go back and read up on selection sort, it skips last spot since it will be in the correct spot after checking the second to last spot. So we don't need to actually check the last spot. And so this says, okay, find the max element in what's left, store the current one into max right now, and record its position. And then starting at the next spot to the right, next element, looking at the next element, and going until we get to the end. Do max compare to. Now these are objects, so we need a compare to method rather than less than or greater than. So if max compare to, if this is greater, then it gives a positive. So if max is greater than this, it gives a positive. So if it's negative, that means we've found a new max, and we should store it and record its position. But then we got to keep looking until we've gone through the whole thing and found really what is the maximum, what's left. And then once we're done and we feel confident that we have the maximum of the rest of the array, we do a swap. So that's just the code for selection sort for a descending order, greatest to least. If an array of integer contains the following elements, what would the array look like after the third pass? So we go through it once, twice, 3 times. What's this going to look like? It's not going to be fully done sorted because we need to make as many passes as there are elements to ensure it's sorted. So after the first one, at the beginning of the first one, this is what we have. And it says, okay, let's put this into max and let's look through the rest of it, every single item. If we find anything bigger, it's the new max until we're done. And then it swaps these. So after the first pass, we're at 109, 42, -3, 13, 89, 70, and 2. That's after the first pass. So now the second pass starts in the next spot. That's for sure in the right spot. So it starts here, sets that to max, looks for the max and the rest of it, and swaps those. So after the second pass, 2 things are in the right order, but you gotta follow the swap. So now we check this one and we look for the biggest one left, and it swaps those. So this is the third time. So this is where we're at after the third pass. The first 3 elements are in order, but you also need to know where everything else stands. But we're looking for this answer: 109, 89, 70, 13, 42, -3, 2. That is A. So that's how selection sort works. Looks for the biggest thing, puts it in the spot. Looks for the next biggest one, puts it in the spot. But it does a swap with the one it finds. Number 9. Refer to the method search, initialized array variables, key, the value to be found, return the value of k such that k is between -1 or equal to and the length. It's going to return -1 if it doesn't find it. It's going to return something greater than or equal to 0, but less than or equal to the last index if it finds it. So it's kind of normal return post condition for any kind of search method. -1 is a common return if it's not there. So search, we have a array of integers and a key. Key is the thing we're looking for. That's a common name for the thing you're looking for. Index equals 0. We can do a while loop. While index is less than the length, that's good to check to make sure we don't get out of bounds error, and the index is less than the key, then keep looking. Now, did it say anything about this being sorted? Because I feel like that would really rely on it being sorted. Because as soon as this is the thing you're looking for is bigger than or equal to the key, it stops. And then it says, well, if they're equal, return it. Otherwise, we got through the whole list and didn't find it and return -1. Assuming that the method works as intended, which of the following should be added to the precondition? That's what I said. Precondition. That it's sorted. Now, which way? Smallest, largest, largest, smallest. So this is saying if the current spot is less than the key, then keep looking. That means the key is bigger than it and we haven't found it yet. That would be in increasing order. Ascending. Smallest to largest. Okay? Not largest, smallest, unsorted. It just wouldn't work at all. There's at least one currency key in V. That's not a requirement. It might not be there. Key occurs no more than once. That doesn't matter. It'll just find the first occurrence of it. Does that make sense? So this is like a sequential search with a sorted array, and it bails as soon as it's looked for all the values. 1014. For the following binary search method, private instance variable. So we have an integer arrays sorted in ascending order. So we're assuming that's true. We're looking for that. Once it's done, index has been returned such that the spot equals the thing we're looking for, or -1 if it wasn't there. So this is binary search. So this is like the guts of a binary search code. Starts with low at 0 and high at the upper end. And while the low end of where we're looking for, so this is like the low end of where we're looking for, and this is the high end of where we're looking for as far as locations in indices. As long as low is less than or equal to high, then we're going to look at the midpoint by adding low and high and dividing by 2 and check to see if it is. And if it is, return it. Otherwise, if the middle is lower than the key, then that means we must look to the right half. And so we're going to set low equal to mid plus 1 as the new low and look in the right half. Otherwise, if this is false, that means that mid is bigger than key, and key must be to the left of it in the first half. So we set the high equal to mid minus 1 and leave low at 0. And then if we get through all of this and we never return anything, then we just automatically return -1 because we for sure didn't find it. So this is how binary search works. It cuts it in half, looks in the right or left half, cuts it in half again, keeps going until it finds it. So binary search will be performed on the following list. To find the key of 27. So we're looking for 27. The search interval after the first pass through the while loop will be what? So search interval means where are we looking for? So the first time, low equals 0, high equals 7, mid equals 0 plus 7 divided by 2, which is 7 over 2, which is 3, because it truncates it because they're integers. Doesn't give you 3.5, and that would make sense as a location to look for anyways. So it checks this spot right here, right? And it's not equal to it. So what it does is, this is still in the first pass, it it either resets low or resets high. Now, because 11 is less than 27, it says, you know what? We need to look over here. So it resets low equal to mid plus 1. So it resets that. So now we're looking at 4 to 7. 4 to 7. So that's how binary works, okay, with the low, high, and the mid. How many iterations were required to determine that 27 is not in the list? Well, that's the first iteration, right? So the next one is low equals 4, high equals 7, mid equals 4 plus 7 over 2 is 11 over 2 is 5. So it checks this spot on the second iteration, and it's not equal to it. And this is smaller than the value we're looking for, it says. So it says, you know what? You need to look to the right. So it sets low equal to mid plus 1 to 6. High stays the same. And then your new mid is going to be 6 plus 7 over 2 is 13 over 2 is 6. So it checks this spot, right? Now, it's not equal to it, but this spot's bigger than that. So when this is bigger than that, then it says, you know what? The new high is going to be to the left of this. So it leaves low the same, and it resets high equal to mid, previous mid minus 1. Then it goes back into the search and says, well, as long as low is less than or equal to high, then keep searching. But as soon as they pass each other, then it's not there. You've missed it. So 1, 2, 3 iterations. Because at this point, it's done. It's not in there. It returns a -1. Okay. What will be stored in Y after executing the following? Well, it says that it's looking for 4, and what binary search returns is it returns the location. So where's 4 at? Where is 4 at? It's at location 0. Right? So that's it. That's what it returns. It returns the location, and it's there. If it wasn't there, it would return -1. So next two problems are still referring to the same code. If the test and while loop is changed to if low is less than high, the binary search method does not work as intended. Which value in the given list will not be found? Now this is where it got rid of the or equals to. So it is possible that you might get a spot where low and high equal each other, and so then mid equals the same number, and it could be at that spot. So I don't know if there's a better way to do this, but we could just try and see what happens with each of these. It's like you're just checking each answer. So I'll let you know that we get lucky. I don't know if there's a better way to do this, but if we're looking for 4, let's just start with that. It would say low equals 0, high equals 7, mid equals 3. And so it checks there, and it's not there. But 4 is less than that. So then it says, let's look at the left half. So low stays 0, but high gets shifted to just the left of the right half to 2, mid minus 1. Then mid equals 1. So it checks that spot, and it's not there. So then it says, well, it must be to the left because this is bigger than what we're looking for. So low stays what it is, and high gets moved to 1 less than mid, which would be 0, and then mid, the new mid would be 0, and that is where it's at. But the problem is that low is not less than high if you don't have the or equals to, and it fails to find it. So this first example right here doesn't find it. Now, I don't know if there's a more I don't know if it's like the extreme cases. This could happen I think in a lot of different places in here. But that one for sure doesn't work. Number 14, for binary search, which of the following assertions will be true following every iteration of the while loop? So what's going to be true at the end of each while loop? Okay, that key equals mid or key is not an A? No, not yet. I mean, this is still in the, like, every time we go through the while loop, we're still looking for it. That just because we're at the end of one of the while loops doesn't mean we found it or it's not in there. That the key is less than or equal to low, that it's somewhere in between here. Not necessarily. The key could be beyond the lowest value or above the biggest value. That mid is less than or equal to high. No, there's some cases. We did one up here where high was smaller than low, right? And so this isn't, like, so the first one, my notes is haven't found it yet. Okay, it's a little premature to say that. Next one is it might not be in the list. So that's not for sure true. This one is no. If it's not there, if it's not in the list, it's possible that high might end up less than low, or low might end up bigger than high. Okay. Now they're saying either it is there at mid, or it's somewhere in between, or it's not there. And so the last one's right because it describes all the three possibilities. It's either right there, it's somewhere in between, or it's not in there at all. Okay, 15 is not referring to that same group of problems. A large sorted array of 30,000 elements is to be searched for a value key using an iterative binary search. Assuming that key is in the array, which of the following is the closest, smallest number of iterations to guarantee that it's found? Worst case scenario, essentially, is what they're saying. Now, remember, binary cuts in half, cuts in half, cuts in half. So they have this little trick, and they're kind of trying to help you out here, that if you can figure out what 30,000 is equal to 2 to what power, that power will give you the number, worst case, maximum number of iterations to find it. If it has to, like, totally doesn't find it until the very end. Now, you could say, okay, well, they're kind of helping you out right here. 1,000 is 10 to the third, is 10 to the third, and they're saying that's about 2 to the 10th. Now, 30 is close to 32, which is about 2 to the 5th. And rules of exponents say that you would add these. And so you could use that approach if you remember that trick. But it's actually not too hard to just kind of break down and say, okay, well, first case, there's 30,000 elements, and then we cut it in half, and now there's 15,000, and then there's 7,500, and then there's 3,750, and then there's 1,875, and then there's 937.5, but it truncates it. Half of this would be 460, 8.5, 234, 117, 50, 8.5, 29, 14.5, 7, 3.5, 1.5. So now we're down to, there's only one left. So it's either there or not. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, that works too. Because we're cutting in half repeatedly. Worst case scenario is we have to cut it in half so many times that we finally get down to a chunk that's only one element big, and then you're done, right? So there's a couple more questions that comes up on that trick works on. Either look for 2 to, now round up to the nearest 2 to a power, and then that exponent is your worst case scenario. 16 to 19 says, refer to the following information, consider insertion sort. So insertion sort goes through and just starts putting things into the right spot and starts creating a sorted list, and then there's an unsorted list, and it keeps taking one more thing and putting it in the right order on the other sorted part, and eventually it's all done. So it says it's unsorted, integer objects, and then we want it to be sorted in descending order when we're done. So the code changes slightly for descending or ascending. Descending is biggest to smallest. Ascending is going up, smallest to biggest. So insertion sort is a for loop, starts at 1, so it skips 0 because it says, okay, well, the first one is already in order with itself, so we don't need to look at the first one. And it goes through the whole thing, and it creates a temporary variable to hold the current spot, and then it creates another variable, j equals I minus 1. And so what this does is it says, okay, let's look. So it starts at next spot to the left, or the previous spot of where we're at. And it says, okay, while j is greater than or equal to 0, and temp, the current one, is bigger than this, so greater than is going to give you a positive. So, and we'll see how this works in a second. If as long as we have it gotten to the end of the array, this is like to keep you from going out of bounds, and the current one is bigger than this one, then we haven't found the spot for temp to go, because we need to wait till we find a spot that's bigger than it, and then we'll put it right afterwards. So what it does is it pulls this one out of the array, and it starts shifting everything to the left. It says, okay, well, the next spot equals the previous spot. And so this gets put into that spot, but we're holding this in this temporary variable, so we haven't lost it. And then we decrement j, and we look in the next spot, and we keep doing that until we find one that's bigger than that, and then we say, okay, well, that's the spot we're going to put temp. So we've scooted all the ones to the right one spot until we find the right spot for it. So here it says an array integer is to be sorted biggest to smallest using insertion sort method. If the array originally contains 1, 7, 9, 5, 4, 12, what will it look like after the third pass? So the first pass, the indices are 0, 1, 2, 3, 4, 5. And the first pass just looks at this spot. We skip the first one. Like I said, that one's already going to be sorted on its own at that point. So we look here and we say, okay, we save this. We say, is this, say, is this one bigger than this? And the answer is no. So we scoot it down, and then we put 7 here because now we're at 0. So after the first pass, it looks like this: 7, 1, 9, 5, 4, 12. Okay, so then that would mean that the first two are sorted in correct order for themselves. So then we look at this one and we say, okay, is this one bigger than this one? Nope, so scoot it down. Is this one bigger than this one? Nope, so scoot it down. And then now we're at j equals 0, so that's where the 9 goes. So this is after the second pass. It's going to be 9, 7, 1, 5, 4, 12. So in the third pass, it says, okay, well, we've already gone through the first 3. So we're going to start here at 3. We can say, is this bigger than this? Nope. Let's go down. Is this bigger than this? Yes. So then the 5 goes right here. So we get 9, 7, 5, 1, 4, 12. So after the third pass, this is where we're at. 9, 7, 5, 1, 4, 12. B. So that's how insertion sort works. When sorted big to small with insertion sort, which list will need the fewest changes of position for individual elements? Now, these are tedious. I mean, if you look at Barron's explanation, they say, oh, well, which one, it says fewest changes. So which one's going to require the least amount of work to get it sorted using insertion sort? And they say, well, there's this one in here where most of them are already in descending order. It has the least amount of ones that are not in descending order. So that's your best case. And I think they point out that this one, everything's in order except for this one. So that's your best case scenario out of all these. Otherwise, you could go through and start counting all the different changes it requires. Now, when I did this, I get kind of a tie for the two least. So I might be missing something, but still an interesting exercise to do. So I'm kind of doing what I did up here, but I'm going to do it till it's done. And I'm going to try and get really good and fast at this. So the first one, it looks here. It says, this is bigger. Yep, everything's good. So that's 0 changes. And then so I go to the next one, and we look here and we say, well, this one has to get scooted down. The 2 goes here. I would consider that 2 changes. So now we have 5, 2, 1, 3, 4, 9. So then we look here and we say, oh, this one has to get moved down. This guy has to get moved down there. So I'd say that's 3 changes. So now we have 5, 3, 2, 1, 4, 9. Now we look at 4 and we say, oh, we got to move this, move this, move this, and put the 4 here. So I say, well, that's 4 changes. So now we have 5, 4, 3, 2, 1, 9. Then we look at the 9 and say, well, we're going to move this down, 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 put the 9 there. So I say 1, 2, 3, 4, 5, 6 changes. So I'm like, that's a total of 15 changes for the first one. If I did that right. Okay. 1, 2, 3, 4, 5, 6. I don't know. Okay. So we can look at the next one. Now you can see this is tedious because I'm going to have to do this for every single one of them. I mean, maybe if we were like, there's a couple that seem worse than the others, or better than the others, maybe we'll just check those. This one says, okay, well, look at this. And it checks that. And I say 0 changes, right? And then this one says, okay, look at this one. Oh, we got no, that one's also 0 changes. Everything's in order, descending. And then we look here and we say, well, we got to move this one down, put the 4 there. So I'd say, oh, that's 2 changes. Then we look at this spot and we say, oh, we got to move this down, move this here. So I'd say, well, that's 2 more changes. Then we look here, we say, we got to move this down, move the 2 here. I say, oh, that's 2 more changes. So I say total of 6 changes. So obviously a lot better. So then we can look at the next one, 9, 4, 2, 5, 1, 3. Look here, 0 changes. Then we say, all right, 9, 4, 2, 5, 1, 3. We're going to look here, 0 changes. 9, 4, 2, 5, 1, 3. We look here, we say, oh, we got to move this down, and put the 5 here. So that's 3 changes. Then 9, 5, 4, 2, 1, 3. And we look here, we say, oh, 0 changes. Then 9, 5, 4, 2, 1, 3. We look here, like 1, 2, 3 changes. So I get 6 changes. So I get a tie between B and C. That's where I get stuck. So I don't know. Maybe someone could explain to me what's going on. But we could keep doing this for the others. 9, 3, 5, 1, 4, 2. And you could do something like that on 18 also, because you're looking for the greatest number. But the greatest number would be the one that's the most out of order, or maybe the most in reverse order from what you're trying to get. And so what's the one that looks like it's mostly in ascending order? 1, 2, 3, 4, 7, 6. I mean, most of that is in ascending order, whereas this is kind of going down. This is kind of going down. This is kind of a mix. It's going down. That's going down. So I think their logic is, well, that one's the most in backwards order. So it's going to take the most comparison and most swaps to get it all rearranged. But the way I did it was I started doing the work like I was showing you right there. And so I got 29, and then I got 6, I got 10, I got 8 moves, and I got 20. So this one was the worst one when I tried to count the number of changes like I did up here, but this one's even bigger. This one has 8 elements, whereas these just had 6. So this is going to be even more work than these. I don't know, but I'm not going to waste your guys' time anymore, but that's how I did inside, which makes you really get understanding that the way it works. So there's a benefit to that. All right, 19. While typing the insertion sort method, programmer by mistake enters this instead of this. So they forget to check for out of bounds, which doesn't mean it's going to fail every time. It's going to fail, I think, if it's not in the list. That's the main thing. Despite this mistake, the method works as intended the first time the program enters an array to be sorted in descending order. Which of the following could explain why it worked? Well, we're trying to go descending order. So it could already be in descending order, right? And the first element could be the largest one already, because this says at first temp is going to be largest, and it says if temp is bigger than the next one, then keep going. So if temp is already the largest, then let's see, it doesn't make sure steps. Okay, so what this does is this stops. Let's see if we can write down this logic. Stops if element is bigger than all the elements to the left of it. Okay, so you guys remember how this works. It looks at a spot and compares it to all the spots to the left of it, and then compares it to all the spots to the left of it. So if it's bigger than all of them, wouldn't it keep checking? I don't know. The right answer, by the way, is D. It's 1 and 2. The first element was less than or equal to all the other elements in the array. That's the other case. We're trying to go descending order. And we could look at, didn't they give us the code for, so like this is the code right here, right? So it says, starts at the next spot to the left if J and temp temp is, I don't know. I'm stuck right now. Hold on, let me pause this. Okay, so I tried to think about this a little more. This stops if the current element is bigger than what's in temp. And then it stops. So if the first thing in the list is the biggest thing, then it'll hit that, say, oh, well, that's bigger than our current one. We're done. So it'll work if the largest element's in the first spot. Now, descending order would also agree with that. If it's already in descending order, then the largest element's in the first spot. But that's the key. Okay. 20 says the elements in a long list of integers are roughly sorted in decreasing orders. No more than 5% of the elements are out of order. Which of the following is a valid reason for using insertion sort rather than selection sort to sort this list in decreasing order? So insertion sort is what we've been doing, where it looks for the next biggest thing and puts it there. Selection sort looks for the next biggest in the whole rest of the list and puts it there instead of just inserting the next spot into the right spot, it looks for the next perfect thing. Now it says that insertion would be better than. It's already kind of roughly. There will be fewer comparisons. Selection sort compares all the rest of the list over and over and over again. So I think this would be true. That potentially, because selection sort has to check all remaining spots, whereas insertion sort just goes one at a time with the previous spots that are already sorted. And once it finds its right spot, it stops. So that's where it gains some less comparisons. There will be fewer changes in position, not necessarily differences in changes in position. There will be less space required. No, space isn't the issue here. So it's going to just be one. Now, the optional topics, we're not going to bother with. Okay. And it said optional topic. Those are going into some searching and sorting algorithms that are not covered on the AP calculus, AP computer science A exam. So we're not going to talk about them here. We got enough on our plate as it is. 22. Which of the following is a valid reason why merge sort is better than insertion sort for randomly ordered lists? Well, merge sort requires less code. No, it has quite a bit of code. Merge sort requires less storage. For sure, no. Merge sort definitely needs storage. Merge sort runs faster. Yes, for large arrays, because what it does is, so the storage thing, by the way, merge sort needs a temporary array. It can take up a lot of, memory is definitely an issue if you remember the presentations. So it's definitely not less storage. It's a divide and conquer strategy, right? So it looks at each spot, I think like once or something, or definitely a lot less than insertion sort. So I'm going to go with 3. Let's see. (23) A large array of lowercase characters or searching for PQRS. The first step in a very efficient searching algorithm is to look for characters with this. So they're saying which one of these is efficient. This one, they're saying look at each spot for P. That's pretty much sequential. That's not very efficient. That's pretty much the least efficient. Okay, not efficient. This one says look at 0, 1, 2 for any of the letters in P, Q, R, or S. I'm like, that doesn't seem any better than A. You're looking at every spot. This one says, all right, skip 0, 1, 2, check 3. Skip 4, 5, 6, check 7. And look until you find an S, which is the last letter. So it's kind of like saying, well, let's look at groups of 4 and see if we find an S. The problem with that is that you might miss it. Like, let's say that it was A, P, Q, R, S, and you're like, there's no S, so let's go to the next one. You just totally missed it. So that's assuming that like the PQRS and other things that aren't PQRS are all in chunks of 4, which it doesn't say. So this one could totally miss it. This one says do the same thing, but look for any letter PQ or PQR or S. Well, that would find it. If you're looking at every chunk of 4 for any of these letters, then you start to look at the letters around it if you find one. So I think this one would work, and it would cut down. If you search 4 later and you don't find any of them, then you don't need to check any of the 3 before it. Like you for sure didn't find it. And then you check the next one. And if it's not one of those, then you for sure don't need to check those. So this would save us time. This one says to do the same thing until any letter other than PQRS is encountered. That doesn't make sense. So you're looking for the thing that doesn't work. I don't know. So it's going to be D. It's kind of an interesting algorithm to try and cut down on comparisons. 24, the array names is a list of 10,000 name strings. List is to be searched to determine the location X, which of the following preconditions is necessary for binary search. There are no duplicate names? No. Number of names in the list is large? Doesn't have to be. List has to be in order. Binary requires that the list is sorted. If it's not, binary doesn't work. Okay? So, 25, consider the following method. Precondition contains integers. Some method, you give the array of integers, you give it in value, int in, which is the size of the array. And then you give it a value. And it says if n equals 0, return -1. So that means this is your base case. This is a recursive thing. That means we've gotten to the end and we never found it, return -1. Else, we're going to start, I think, at n. And now n is the size of the array, so n minus 1 is the last spot. So we're going to check the last spot first. Okay, and see if it's there. If it's not, if we do find it, then we return that. We found it. Hey, this is it. If it's not there, then we're going to call the same method again using the next spot down. So essentially, we're going to check the last spot, then the second last spot, then the third last spot, then the fourth last spot until you find it. And if you get all the way down to 0, that means you didn't find it. The method shown is an example of, this is just looking at every single spot till you find it. That's sequential search. Now it's taking advantage of the fact that it's not taking advantage of anything. It's looking at every spot until you find it. That's sequential search. Not efficient, but very straightforward. We're going to skip 26. 27. Assume that merge sort will be used to sort an array of integers in increasing order. What's the purpose of the merge method? So this is just where you know the merge thing is that merge sort splits it in half, splits all the arrays in half and half and half until they get all the way down to size 1, and then it starts putting them back together in the right order. And that's where the merge works. The merge is putting them back together in the right order. It partitions it into 2 parts. No, that's the kind of half. It uses recursive algorithm to sort them in increasing order. No. It divides array into n subarrays. No. It merges 2 sorted parts into a single sorted array. And this one sounds a lot like it. It merges 2 sorted arrays into a temporary array that is assorted. And the thing that's wrong here is that when you give it to merge sort, it starts with a single array. So it's given a single array with 2 sorted parts. So the first part is sorted, the second part sorted, and then it puts them back together all in that one array sorted. So that's the major difference here. But D and E are the only ones that are even close. A binary search to perform on 600 elements, worst case. So this is that thing of like 2 to what power equals 600. Round up to the nearest power of 2. Now, if you could figure that out, you could be like, well, 2 to the first, 2 to the 0 is 1, 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, 2 to the fourth is 16, 2 to the fifth is 32. I mean, you could do that, I don't know, 2 to the sixth is 64, 2 to the seventh is 128, 2 to the eighth is 256, 2 to the ninth is 512, 2 to the 10th is 10,024. Oh, I think we passed it. Yeah, well, no, that's it. That'd be 10. That's the next large power 2 that's bigger than that. The other way of doing it is to just split in half and be like, all right, starting with 600, it cuts it in half. Cuts it in half, cuts it in half until it finds it. Worst case scenario, it keeps cutting it in half, truncates it, 18.5 truncates at 9, 4.5 truncates at 2, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I kind of think that's maybe faster than doing all these powers of twos. Unless you just remember some of these powers of twos quickly in your head, then you can kind of skip further down the list. But that's that same trick that came up again. That's why 600 elements, worst case scenario, takes 10 steps. Sequential would take 600 steps, right? So worst case situation for insertion sort would be what? So insertion sort is where it's looking and looks at the first part, puts in the right spot, looks at the next part, puts it in the right spot, looks at the next part, puts it in the right spot. So probably best case scenario is that it's already sorted, right? A list is in corrected sorted order. It's in reverse order. This is like worst case for insertion sort because it's in random order. This is kind of like in the middle. But so we're looking for worst case scenario. Well, that's when it's in reverse order. That takes the most work. Most comparisons, most movements. 30, consider binary search ordered list. Which of the following choices is closest to the maximum number of times? So this is worst case scenario for 1,000,000. This is just like what we did in 28. So you have two options. You could either do powers of 2, or you could cut in half till you get down to 1. So I'll do that one. 500,000, 250,000, 125,000, 62,250, 31,125, 15,500. Make sure I'm doing this right. Let's see. 1,500,000, 250, 125, 62,500. That's what that's supposed to be. 62,500. I mean, if you mess up, you probably get close. These numbers are all pretty far apart. 31,250, 15,625, 78, 12.5, 3906. 1953, 976.2, 454, 83, 88, 244, 122, 61, 30.5, 15, 7.5, 3.5, 1.5. So, I mean, I think this will be close enough. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Well, if you were like, oh, is it 21 or 19 or 18 or 25? Like, that'd be the closest one. So that, or you find the nearest power of 2 that gives you 1,000,000, but over 1,000,000. 31, consider these three tasks: a sequential search of an array of names, pretty inefficient; a binary search of an array of names in alphabetical order, much more efficient; an insertion sort into an alphabetical order of array in names that are initially in random order. For large N, which of the following listed tasks in order from least to greatest of their average case runtimes? So runtimes. I mean, this has to look at, now these aren't even comparable jobs, by the way. So don't, sorting is different than searching through it, So you have to look at each spot once, right? This is probably the best. Insertion sort is looking at each spot probably lots of times, multiple times. So this is your worst as far as comparing these all to each other, as far as the amount of work they have to do, even though they're totally different kinds of jobs. I mean, these are comparable. You're able to compare these to each other, and this is way better than that. But then sorting is totally different than searching. So least to greatest average case time. So we want 2 to be the first one. So that gets rid of that, and that. And then we want 1 and then 3. Okay, 20, 32, and 33 are optional. So we're skipping those. Skipping to the last page. Okay, so all these questions are referring to this high-low game. Because they're a high-low game, which the user thinks an integer 1 to 100, saying like, guess a number. Each time the computer makes a guess, the user says either, it's lower than what you said, it's higher, or you got it. So they're kind of giving you a little bit of a feedback on the high-low game. Suppose, and that kind of makes me think right away, oh, I should use like a binary, approach or something. Like I'm going to guess right in the middle, and then I'll adjust my guess. Otherwise, I could just randomly guess, even though they're giving me these hints. Suppose the game is programmed so that the computer uses a binary search, hey, surprise, for making its guesses. What's the maximum number of guesses the computer make before using it? This is that same problem. There's 100 things. So 50, 25, 12.5, 6, 3, 1.5, 1, 2, 3, 4, 5, 6, 7. Worst case scenario. Or you could say, what's the closest power of 2 equal to 100? You'd be like, well, 2 to the 5th is 32, and 2 to the 6th is 64, and 2 to the 7th is 128. So you want to round up. There we go. Now, there was another number that was really close to it, but that's that same thing. 35, suppose a computer use a sequential search strategy for the guessing. What's the maximum number of guesses the computer can make before getting right? Sequential search is going to look for every spot. What if it's 100, the last spot? They might have to guess every single number if they just go in order. Using sequential search strategy, how many guesses on average? Well, on average, you could get it on the first guess, you could get it on the last guess, you could get in between. So on average, it's going to be half the size of the array. On average, they'll get it, within half of the array. Sometimes sooner, sometimes later. That's it. I hope you guys now are feeling better about searching and sorting.